Okay, so our first presenter for this meeting is Jeff Baker. Doesn't need an introduction, but I'm going to do an introduction for him anyway. So Jeff received his master's degree at the University of Waterloo, studying fenestration heat transfer. Jeff spent 30 plus years working in the fenestration energy analysis field. Jeff's president of Westlab Canada, running one of the largest fenestration simulation organizations. Jeff is the ombudsman and former chair of NFRC, vice chair of the CSA for 40 Technical Committee on Fenestration Performance, vice chair of CSA for 40.2 Subcommittee on Fenestration Energy Performance, and participates in several Canadian National Building Code committees. Well, not only a window geek, Jeff's also a serious photography geek as well. So Jeff, come on up. I've got a presentation we're loading up for him, and we'll get her going.
Thank you, Terry. It's great to be back at Fenestration Canada. And yeah, serious window geek, you will believe me by the time I'm done this presentation, trust me. We're going to take a deep dive into some data and take a look at some things. Just before we get, as Terry's pulling this up, oh yeah, okay. Little history before I get started. Back in late 2017, early 2018, Natural Resources Canada came out with their aspirational goal to get to a U factor on a window of 8.2 metric or 0.14 inch pound by 2030. So they put that out there. There was lots of work. There was participation by FenCan and many others in the industry to look at this and push forward. That is coming through into the code. It looks like that's where things will be going. I'm going to show you some of that data as we move through here today. No, it's moving. We're good. So that was some of what they called part of their market transformation. I'm just going to cover a bit of the history of that, where it came from, where things are going. Then what I'm really presenting is some work NRCan paid me to do on research into the barriers of getting to these values. It's a two-phase study. You're seeing the second phase data was, well, the final report's not done because it was only submitted last week. But I'm going to share some of that data, and that's the deep dive into triple glazing that they asked me to take a look at. So we'll do some Energy Star history, the Pan-Canadian Framework, and the National Net Zero Climate Change and Resiliency by 2050. If energy requirements bother you, carbon is going to terrify us, okay? I'll touch briefly on that. I haven't got a lot on that one. So if you go back and look at the history of Energy Star, we went from 4 zones to 3 zones to a single zone by version 5, which was brought out in 2020, January 1, 2020. And I just sort of tried to well, that's all the data of the history of it, but it there's what's happened over time. Energy rating on the right, U factor on the left, and you can see just over time what's happened in the regions. And it's just driving energy rating up, pulling energy rating U factors down.
Well, Mike, I have calls all day. That's the problem.
So they have historically been on a 5-year cycle. So they would be due to change the program in 2025. I can tell you, relax a little bit, that's not going to happen. It will be late. There's some things going on at Fenestration, at NRCan in the Energy Star group, and they will be delayed on that. I can assure you of that. Whether it's 2026 or later, I can't tell you right now, but I do know that some changes have gone on. Our old friend Steve Hopwood is back on contract with them again to go back in and teach them some things because they lost a lot of their staff. But that's what's been going on in that group at NRCan. I'm working with CanMet, their research arm, on this, so they are pushing forward with some work on Windows. So, so the Pan-Canadian Framework on Clean Growth and Climate Change was signed by all the provinces and territories to push forward. In the medium term, they were looking for U factors of 1.22 or an energy rating of 34, and then 0.82 in inch pounds of 0.14. Some of the Americans, Brad's in the room, a 0.14 U factor, that's huge, a huge deal to try and get to that level. We're going to talk a little bit about that. So that's the long-term goals. All that work on what they were doing and what they were trying to do to achieve that I can't find anybody in NRCan to talk to about that these days. But it's definitely been picked up and being driven by the codes right now, and I'll focus on that as we move through here. There's some history in there of when all of this took place. But the one that's becoming more important right now is the net zero and climate resiliency work on building strategy. So there's a commitment in the building code to trying to get to net zero carbon or greenhouse gas emission by 2050. And I can tell you they're pushing really hard at the code. How this will implement, how it will phase out across the country. Right now, they're looking at getting operational carbon requirements into the code for 2025. Well, from the window perspective, that's a good thing. Lower energy windows reduce the operational carbon, and windows look even better on that perspective. 2030, they want to put embedded carbon in the materials into the code. So for 2030, embedded carbon, that's going to be a very big challenge on what they're going to try to do with the code. Well, they're also trying to get to these ridiculously low U factors by 2030. That's going to mean triple glazing. So what's the carbon content? Oh, what's the carbon factor on adding the extra layer of glass? All of these are discussions going on right now in many different places. So this particular research into the barriers was to take a deep dive into the data, see what's out there right now. And let me first and foremost clarify, the data I'm going to present is what's listed in either the Energy Star database or the NFRC database, okay? It does not mean that they're available right now. It's what manufacturers have listed and potentially could supply to the industry, okay? I think there's product in there that could be there, but I'll qualify right now. Anybody that's got data in the system with Krypton is highly unlikely they want to deliver it right now on the price point, or the price point will be so high it'll be a challenge to put it in there. One bottle of Krypton, about 2 years ago, I was told it was worth $30,000. About 12 months ago, it was over 60. Somebody told me it had a great price drop. It's back down to near 40 is what I've heard just recently. But I just heard somebody say 75 out there. If you know that and you're looking, I might be talking US dollars. But it doesn't make sense. Like to put it in right now, but we'll see where that becomes relevant as we go through the data. So key things we looked at in the data was trying to filter through, look at the framing materials, number of glazings. This was the first phase of the study. Number of glazings being used, the overall thickness of the IG, spacer system type, gas fills, and the percent frame area. And this becomes important because when you move on, even at double glazed levels in a lot of windows, the center of glass is better than the frame in a lot of cases. So if you can increase the glass area by reducing frame, then I'll also qualify right up front. I talk a lot about energy. Anything you might do to redesign a frame, if it doesn't meet air water structural requirements, it's not going to work for you anyway. So you've got to look at all of that. So in this deep dive into the data, we took a look and broke it down to U factors sort of less than or equal to 1.50, 0.94, and 0.82, and went through and looked at that data, what was in the database. Maybe I'll pre-answer a question. Are you going to supply copies of the presentation to the members?
All of the presentations that we do are going to be on our website.
Okay. So I'll get Terry the PDF version of this so that it can be put out there. So the goal of this study was just to better understand this. What would it take? So what I've added in over here is this is a possible requirement going into the 2025 National Code. Now, the things about the code you need to understand, unfortunately, I wasn't here for the discussion of the BC code yesterday. I was up in my room on a national code call dealing with some of this stuff. But the tiered code or the stepped code that BC has had in place for a while now, that's in the 2020 National Code has done that. So Tier 5 is the upper level. They're writing prescriptive requirements to qualify for Tier 5 in the National Code. This is the potential numbers they're looking at. Real important. That says possible changes, okay? It's not final. Make that real clear up front. But those are the kinds of numbers. That just happens to coincide with the numbers we were researching in sort of those categories as well. And then also, did I mess this up? I did mess this up. No, that's right. Okay. So to better understand that data, this is all the Energy Star data plotted on a graph. Across the bottom is U factor, up the vertical is the solar heat gain. Turns out that line right there is the energy rating value, okay? So it looks at that data, and if you look at that data and said, okay, no, I missed a slide somehow, because is this gonna work? Okay, yes, it leads to the next part. Okay, sorry, just got out of sync on that. Lots of people in discussion about high solar gain were very concerned about this data over here on the high solar heat gain, high U factor. But when they did the climate resiliency study and looked at overheating in buildings, they're actually really concerned about the data over here. When you get down to very low U factor and high solar heat gain, it causes a bigger problem in overheating than this does over here. So at the code level, to address, it became a mandate to deal with potential overheating issues. And they jammed that into the 2025 code about less than 12 months ago. And we're mid-cycle, it's a real challenge. So what are they gonna do about it? They're talking about introducing into the code a possible, again, this is a possible limit, if you are less than 17%, FDWR, if you don't know that term, is fenestration and door, because in that code, they don't understand that doors are part of fenestration. So they define fenestration and doors in the national code to wall ratio, okay? So if you're less than 17% on a given orientation, not the whole building, so it looks at each orientation, they are looking at putting a cap on the prescriptive compliance path in the code of a 4.5 solar heat gain. If you're 17 to 22, it would be 4.0. If you're greater than 22, originally they were gonna kick you over to the performance path, but at the last minute they said, well, the performance path in the reference house uses a 0.26. So if you're less than 0.26, above 22%, you could do that. That is going to come out in a code change request very likely in the fall, October to December, I believe that review period will be. So what does that mean? If we go back and look at the Energy Star data, well, if we capped it at 45, what that would say is that would leave 91% of the data that's in the system now would still be there. Drop it to 4.0, you've got 83%. This surprised me when I went and looked at the numbers. If you dropped it to a 0.26, that's still 56% of the data that's in the system right now is there. Mind you, you've gone beyond the energy rating qualification, you're into the U factor qualification with low solar heat gain. So there's data in the system out there that is potentially available. So that's where they're going. I know the Quebec Window Association is very concerned about these numbers. They think they're too low already. My colleague behind me was in a meeting and spoke up and thought he thinks they're still too high. And Terry and I have spent some time together in code meetings now working on some of this. So this is potentially where things may go in the 2025 code. So, taking a look then, what's it take for what's in the system that could qualify for some of these things right now? So a deep dive looking at frame material, gas fill, percent frame area, number of layers, spacer systems, and the overall thickness. It's really tough to present this data, so hang on, we'll go for a ride here. And yeah, I'm proving I'm the window geek, okay? So if we just look at frame materials and break it down, in the most of in fact, all of this data came out of the NFRC database right now because they took too much data out of the Energy Star database. There's just not enough to do a good analysis of the data anymore. So down here, it gives the total number of products listed. So this would be projecting windows. Primarily, it was just awnings and casements I grabbed out of the data to show the number of products listed or options listed there that qualify. And you can see that even under this 0.82 or 0.14 inch pound, there's 230 products listed there that qualify right now. But then it broke it out by frame material. You can see that aluminum thermal break, aluminum vinyl composite, and aluminum clad wood dropped off that list. There were none in there. But then what's really important over here, you can see that when we get into sliding windows, it was a little bit more of a challenge. As you move down those frame material categories, there's still some there, but I'm going to explain where the problem lies with that data a little bit later. And then it just shows sort of a breakdown of the percentages then of what qualified. So there's multiple materials that can qualify, but when you get to that really tough U factor, it'll become absolutely more challenging. Number of glass layers, it just broke it down by doubles, triples, and quads. You can see right away that no doubles qualified for any of those zones listed in there right now on U factor. We were focused on U factor. If you gave the equivalent U factor in some of these categories, I'm pretty sure you might find some, on energy rating, you might find some products in double glaze that could just squeak in if they're using interior facing low E. So a number 2 and a number 4 surface low E and a double, they might squeeze in on U factor. But with a cap on solar heat gain, they may not going forward. So that's glass layers. Gas fill. This is what became really important on the sliding windows, is you could see that when we get out to the higher performance, like the lower U factors, air and argon fill did not work at all. It was only krypton fill in the sliding windows that could qualify right now of products listed in there. I'm showing some of the quad glaze data because it was there. A lot of that quad glaze data could be products that are triple with a storm panel or a low E storm panel in some cases. So what else did we have here? Spacer systems. You can see that if we look at aluminum, composite aluminum, mild steels, they start to fall off in the highest categories. They exist in others, but many, many manufacturers in the residential sector for sure have shifted over to some form of warm edge spacer. That would make up the vast majority of it. So it was just interesting to take a look at spacer systems that were available. I should mention, all of the data that so far that I'm talking about is in a published NRCan report. Where's Terry? I can probably make that available to you to include with this as well, Terry, so that the membership can see it. And then we'll make arrangements when the second phase is done. I'll make sure you get the report when it goes public. You mean the vinyl clad steel frame? Patio door? Sorry, that was a bit of a shot. If it's heavily reinforced with metal, it will be challenged. Let me back up. It'll be challenged because the framing, hang on, I get back to framing. The framing of vinyl patio doors don't line up as, hang on, have I got it in here? No, I don't show reinforced vinyl window. It would compare well to reinforced vinyl window. If it's a fully reinforced vinyl window, then yes, I would agree with you. But there's just so much reinforcement typically in a vinyl patio door. The framing has a strong component. But if there's alternatives to the metal reinforcement, then it could look a lot better. And I think that as the industry pushes toward these higher performance, it's going to take that kind of level of design to take a look at it to get that to those levels for sure. Mike. A little louder, Mike. Sorry, I can't hear you. I know. You don't hear that often, do you? It's hard to say how deep a dive I did into this. Some of it would, yes, but absolutely it's going to, and hold that question till we get to the design phase later on this, because you're right on top of it. It's going to be a very big challenge. If you want the end result, the glass guys aren't going to be able to fix this problem for you. They've gone as far as they can really, and it's going to take more redesign of framing is the end result of this. So let's get caught up. Where were we? Glass layers, we did that. I'm going the wrong way. Glass layers, gas fills, spacers. Okay, so when we break it down and look at, to get to those higher performance levels, it was taking vinyl wood composites, cellular PVC, vinyl, foam-filled vinyl, and wood products. Unclad wood products could get you there. In some of them, we saw all of those spacers were possible, argon krypton and triple glazing to get to these. So how did it all break down? We go into something called a heat map. And so coming across the top here, I've got the solar heat gain and the different U value categories. And the coloring here, there's a legend over here. As you come down in those colors, the number in each of those cells increases. What's interesting is if you look in the 105, the 94, and the 82 categories, there's lots of data in here, and there's lots of ways to get to that. That's going to be interim code stuff. That's probably levels you're going to need to be at in the 2025 code. And well, let me stop right there for a second. When the 2025 code comes out, the rest of the country is going to learn what BC already knows. That prescriptive requirements to meet code compliance aren't going to be good enough anymore. They're not going to be the cost-effective way to get there. A lot of housing in BC, because they've got this step code in place now, is being designed on the performance path, working with the energy advisors, doing the whole house modeling, all of that work. There's ways that the home builders can find better ways to design the houses. Key and very important in this, triple glazed glass is one of the cheaper alternatives to improve the performance of the whole house. They can almost pay for it. If you drop triples into this house with really good walls, they can almost pay for it in the reduction in the HVAC cost from the prescriptive home by not having to run, HVAC runs out underneath the windows anymore, those kinds of things. So to that level of performance, talking to some of the builders that are trying to build net zero homes now, triple glazed is one of their favorite products. Sorting out all the discussion Al talked about yesterday on overheating and on that, it's quite critical, and we'll touch on some more of that a little later on. But so if you ask me, when the 2025 code comes out, what's the target I need? It'll be tough, except in the tier 5 performance. I can tell you by 2030, that's where they think you're going to need to be in different regions across the country. So this looks at it, and you can see how that dark blue is like between 1 and 10 entries in the database. So when you get down, and this is the projecting windows. When you get down here, there's not a lot of data. Here's the critical thing. That covers argon and krypton. The moment I take the krypton out of that, you can see I lose a lot of data in the lowest level. So again, I've been preaching for a long time. Down in the US, they talk skinny triples. In this country, if somebody's trying to talk you into skinny triples, run away, okay? They don't work. They're going to use them in parts of the US because they can get a little more performance than you can get out of a double in the same frame, okay? But unless you can actually get the krypton into those skinny triples, it's not going to work. If they want to try and work with you and design using that very thin layer of glass in the middle to cut the weight of the triple, but they're optimizing for an argon gas fill, that could work, and I'll show you that a little bit later. How much time do I really have? Okay. Because there's a lot here yet. What was this one? Okay. Just breaking it down to 2 spacer systems. This is still in the projecting windows. You can just see how it starts to filter down on the data, what's actually out there working. What a frame materials, spacers. Oh, this one is percent frame area. Okay, so the change in this graph is across here I've got percent frame area. So somehow there's some windows out there that are 65% frame. I really think that's an error in the database, okay? Because I can't imagine that. But and even at the 50% mark, a deep dive into the data, I've been working with NFRC staff actually after analyzing this data, and they realize there's some work to clean up their data. But one of the trends we'll see, so this is 5 framing materials, triples with argon, bunch of different spacers, is as you move down, the percent frame is getting smaller. So to get to these larger values, the products out there have less frame, more glass. Makes sense? Center of glass U factors are lower than frame. So that's part of the big challenge. And there's a few people in the room I know are aware of that. They've done their design work, and we'll take a look at a deeper dive in that a little later. Okay, this one's overall glass thickness. And it's interesting that it begins to sort of, when you get down to this level, if argon fill only, it's optimizing around, an optimum spacing for argon is around a 1/2 inch, 13 millimeters, thereabouts. So the overall using 3 millimeter glass falls into this category. So when you get to triples, argon filled, you're looking at 213 millimeter, you know, you're 33 to 36 millimeters, somewhere in that range to accommodate that glass. That may work in projecting windows, awnings, casements. Going to be a real challenge to drop that into triples and figure out how to get them to bypass each other. So, okay, so now we take a quick look at the sliding windows. Same thing. I've got 5 different frame materials, but in this slide I'm showing the argon and krypton. If you take out the krypton, you can see what happens down here. I lose everything down here. Sorry. Yeah, if I take out the krypton, nobody has systems that in sliding systems in the system right now that can get to this lowest U factor without going to krypton. So if I back up a slide, all of this data down here, there's 98 of them in total, is all krypton filled. As I say, they're listed there, and I suspect if somebody's got the krypton and wants to build you the IG, if you're willing to pay for it, it could probably happen. But I think you'll find the price on krypton is just so unrealistic at this point. So that will become a problem with sliders. What else we got? So this is triple glazed argon and krypton. Oh, this is percent frame area as well. It's interesting. The percent frame area does sort of center and focus on here. I think some of the limits on the design of the sliding windows in the system today, they all sort of centralize around the same amount just for structural design right now. And there's not a lot of variation. Over time, it will likely be a challenge to figure out how to get more glass into sliding windows, less frame. That's going to be a big challenge. Back to your question, Mike, that is going to be a very large challenge to figure that out, because if you go to less frame, you may need more reinforcement, and figuring all of that out is going to be a very big challenge. And it may come down to figuring out how to reinforce without metals is the big secret, because the metal will definitely increase your U factor. So finding ways around that may be a very big challenge. IG thickness overall, it's interesting when you get down here, it comes in at 27 millimeters. Well, that's keeping in mind that's all krypton. Krypton's ideal spacing is around 9 millimeters, so that's 18 and 3 layers of 3 millimeter glass get you to 27. Anton. No, you raise a really good question, though. When the acoustics come in and you got to go to thicker glass and do other things, the penalty is the airspace on that, and it's going to make it a very big challenge. And I think no work that I have seen been done, acoustics of triples is a little different game too, and how you play that with triples. That's a whole other factor that's got to come into this as well on the energy side. Brad. Highly unlikely going to happen. The political, one of the biggest changes in the code recently is they changed the oversight body at the top of the national code structure. It's all the provinces and territories now have total control. They've agreed from a very high political level to shove this down. So to get permission to do those kinds of things, you'd have to push it back up. And basically their push down is, look at, we want lower energy, lower carbon, and they keep shoving things down from the top. Which has changed the whole code development system in Canada significantly. And it's frustrating. The Canadian Home Builders Association is after some of those things, Brad, and they've had a lot of control in the residential code over the years. They're losing battles. And that's the political will of what's going on right now. Mike. Yeah, please, because I think this is an important question.
So the slide you showed earlier, that's data from the Energy Star website?
No, it's all from the NFR. It's
Sorry.
North American data, though.
Okay, North American data. So on materials you listed up there, we're seeing European window systems come in, large manufacturers that actually meet passive in aluminum using different types of thermal bridging. So that it's not to say. I just want to clarify. The data you put up there is it 100% accurate, or are there, because you got down to 0 on some of the product categories?
Yep.
Yet we're seeing product that's meeting those requirements.
What I'll tell you in that database,
Yeah.
they get down to 0 and there's no product listed that can,
Listed, just listed.
Doesn't mean it can't be done, but it may take a serious redesign in some of the North American designs
Okay.
to make it happen.
All right, so
Yep.
that's listed.
Yeah.
I just wanted to
And
clarify that.
on the
Yep.
stuff coming in from Europe,
Yep.
that's a 45-minute other rant I can do for you one
Yeah,
time if you want.
absolutely.
Okay.
For sure.
Simple answer is, if you have a different standard that measures differently, in one of my presentations, you can't use a yardstick to measure meters and call them the same thing, okay? And that's a simple analogy, that they're using a different standard that measures differently, because if you take any of those European products and run them through the North American system, they will get higher U factors on our scale. And it's just a different measurement structure. Okay. Where am I at? So, after a long review through all of that data, one of the conclusions is, what's it going to take now to hit these targets? Oh, shoot, hit the wrong button. Down here. And I list sort of the elements of the design that are going to be needed. 3 to 4, 4 to 5, or 5 to 6 of these elements are going to be needed to get to that. So low conduction spacers. When I say gas fill, preferably argon, designed to the optimum spacing in the IG. That'll come up again a little bit later. It'll be triples or more. Optimum spacing on the glass, lower frame areas, and new designs in frame materials. And Mike makes a really good point. Where some of those drop to 0 doesn't mean those frame materials can't get there. It just means the current designs in those frame materials can't get there. So, having a discussion at breakfast about Quebec-based aluminum windows with really good thermal breaks. They've still in the market and come a long way, but it may take even more to get down to the really low values. Okay, phase 2 was this deep dive into triple glazing. In this, I was sort of taking this deep dive to better understand Low-E coating location, number of coatings, gas fills. Then we took a look at total products in the same database in the difference in the Low-E configurations being used. Then at the last minute, I was handed could we do a case study of a redesign? And I went, well, not really, because everything I touch proprietary. I can't give that away. Then it hit me. I had a PVC casement window that I bastardized about 15 years ago to do glass and spacer comparisons in, so it was nobody's window, okay? And I went, okay, maybe I tackle that as a redesign. I bit off more than I wanted at that point in time, but I'll show you that in a little bit. And by the way, right up front, I am no window designer, okay? We'll see that in a few minutes. So, taking a look, there's a lot of data here. The slides will get put out. So this one, damn, I made this so small I can't read it now. So what we've got is U factor, solar heat gain, and visible light transmission. Coming across the top, these are all triples optimized at the right, well, they're 35 millimeter overall, so it's going to be around the half-inch gap. They were argon filled and different low-E's. So that would be single silver, double silver, triple silver, low-E. Oh, okay, and the first 3 have got the low-E coatings on surfaces 2 and 5. The next 3 in that graph show up on 2 and 4. And that was talking to manufacturers out there. That's the typical 2 configurations that get built either on 2 and 5 when you're using 2 low-E coatings. Let me double check myself. Yes, that's what we're looking at right now at a 90% argon fill. So you can see that the difference in coating location here isn't that much. So this would be single silver, just different locations. But you do see a small change in the solar heat gain, 0 change in the visible light on those locations. But then when you go from single, double, and triple silver, you can see a radical change in the solar heat gain available, leading into some of the discussions Al had yesterday about selecting the right coating. It's going to be an even bigger challenge when looking at triples, because high solar gain when dropped into a triple gets lower U factors, lower solar gains than the doubles, but they're still pretty high. So there's still work to be done there. One of the things that's coming out of, I can use trade names, eh? Sort of. two of the major glass suppliers, Cardinal and Guardian, are both saying today that when doing triples, it's probably advantageous to, on the number 2 surface, select your solar control. Single, double, triple silver. On the number 5 or number 4 surface, when you're doing that, you're probably better off using single silver there. 2 key reasons. Worst case scenario is if you use 2 triple silver coatings in a triple, the second one does almost nothing for the solar heat gain because the first one did all the work in the solar spectrum, but it really knocks out visible light. It still takes out a significant chunk of visible light. So it keeps the visible light high in the triple, and there's just not a need. And if you can do it that way, single silver is cheaper than the other 2. And total performance doesn't make a lot of, the overall U factor doesn't change that much by using single silver as your second coating. So that was coatings. If we use just comparing 2 coatings to 3 coatings, so now if I go to the extreme, and I need to talk about this because to get to that 0.8 U factor, it's likely going to take, in a lot of designs, 3 low E's to get you there. There's people in the room that have already been down that path and learned this. So in this case, this would be the same 2 layers of single silver. That one's single silver on 2 and 4 and an interior facing low E. So one of the it could be pyrolytic. Typically, you've got Guardian and Cardinal both offering a sputtered coating with a protective layer that can be exposed to the interior environment. It's interesting that we talk about these interior-facing coatings. LOF, more than 20 years ago, was experimenting with this. And one of the downsides of pyrolytic coatings facing the room is their surface roughness is a little bit worse than clear glass, whereas the sputtered coatings with the surface layer, their overcoat layer on the inside is almost the same roughness as glass. Whereas if you get to the pyrolytics, if you try and clean those with a paper towel, you can leave little bits of paper. If you scrape a gold ring across that, there will be a streak, and it takes muriatic acid to get it off the glass. So that is a challenge with pyrolytics facing into the room. So you can see the performance. What's really interesting is when you add that third coating, at single silver coatings, there's a slight reduction in the solar heat gain. In the other 2, it's almost negligible. So that third coating doesn't change the solar heat gain a whole lot, mostly again because the number 2 surface coating did all the work on solar heat gain. Visible light, just a slight reduction as well as you move across to add the third coating. So the improvement is in U factor. The change in solar heat gain and visible light is very small when you get to the triples like that. Okay, we're testing my memory to see what I was putting in here. Comparison of the number of coatings. What the hell? Okay, we'll just move on. Can't remember what that slide was now. So then another part of the study was just to show a comparison across manufacturers. So in the first graph, you've got U factor again. There's 4 different manufacturers here. That's all their single silver, double silver, triple silver. And you can see there's a little bit of variation across the manufacturers. Not a lot, but a little bit. There's greater variation on the single silver than the others. When you get to solar heat gain, it bounces around a little more. And having a discussion with one of the glass manufacturers just recently, sometimes part of the reason that you can't match up across manufacturers is they've all got to work around each other's patents. When they patent how they put the layers down, it means if you get too close to the other guy, you're going to infringe his patent. Well, where that changes more is in the solar heat gain and visible light and how those layers get laid down. So that's part of the reason why the glass changes vary across manufacturers. But you can see it's pretty small. So there's 4 manufacturers listed there. And so the availability of low E, there's lots out there that can happen. So when we looked at gas filling, there's the traditional curve for center of glass U factor as a function of the, this says overall glass thickness or the spacing between the glass. It would have had symmetrical air spaces in the triple. So it just shows the overall with 3mm glass. And you can see the blue curve is air, then argon, then krypton, just to show those. Oh, here's a bonus piece of data. Just recently, been asked this question many times over the years. Well, if I've got some limits, what if I have asymmetric spacing? Okay, so that, I've got room for optimized for half-inch spacing here, but I've got a 1/4 inch in the other cavity. Am I better to do that, or would it be better to have two 3/8 cavities? Definitive answer on a research project that hasn't yet to be published, but should get published, equal air spaces is optimum every time. Every time. And good news for the glass manufacturers, it's way easier to build equal air spaces than asymmetric spacing. So every time, no matter what you're doing, and we dug in, and that study actually was an internal West Lab study. I just need to get it published at some point, because that's an important question to get out there. Terry.
A triple with 12 millimeters and 9 millimeters, and argon and krypton. Have you ever modeled that?
No.
Because now you're reducing your overall cost of the krypton
Yep.
in a triple. Be interesting to see what that
If I
looks
got an
like.
IG manufacturer in the room, would you want to build that product?
Come on.
No, actually, from a practical point of view, I think it would be really hard to build that. But it would. You're right. You could drop some costs, but to get that filled with two different gases could be very challenging. It's even why when you see single low-E coatings, often both cavities are filled with argon gas. The one without the coating, the argon doesn't make a whole lot of difference. But if you're already putting argon in, it's just easier to do both.
There was an IG equipment manufacturer at Vegas a couple of years ago talked about they had the ability to mix argon and krypton into, yeah.
Okay, thank you. Great segue. I didn't pay that man. So there's the traditional curves. If we looked at argon filling, which way do these go? So the bottom one, top down. Oh, sure, of course. The lower the U factor. So it starts at 70, 80, 90, 95, and 97%. I get a lot of questions. In the NFRC documentation, for different ways of filling gas, you can fill to, if you're single probe filling, it's a 90% fill. If you're dual probe filling, it's 95. And if you're vacuum filling, it maxes out at 97. The difference between 95 and 97 is almost impossible to see on this curve. The difference between 90 and 95 is small, but in some cases, it'll be the magic little piece of data that shoves you underneath a U factor, okay? I caution you, what nobody reads in the NFRC documentation, the fill rate in production, okay? That you're gonna claim that you can maintain that in production. I caution you because there are new devices coming into the market that will be able to field test argon filling, okay? That's a little terrifying for this business because there are lawyers that have, more so in the US than Canada, but there are lawyers in the US that have watched developments go up, saw what was wrong, and come along later and say, I know what's wrong with your house. Would you like to sue? So those kinds of things will go on. So argon filling, I think you need to be cautious of. I, in my simulation business, caution my manufacturers not to go beyond 90% unless you really believe you're going to be able to keep that in production and willing to defend that.
Where's the sweet spot of the drop in argon and the relationship to a performance drop?
Anything below 90%. On this curve, you can see it. The bottom lines is 97, 95, 90, and then you jump to 80. So that sweet spot is around 90%. And talking to the manufacturers, filling consistently to 90% is quite doable, and they're confident on that. So in a lot of cases, they're designed to try and hit 95. They're taking 90 just to give them some room in the field when things don't go perfect. So
What about aged units? Because the argon, the spacer is going to be permeable. No matter how impermeable you make it, it's permeable. Doesn't it go down over years?
It does. There is very little research data out there other than a German study that is probably 25 years old now at 1% a year. Okay? But that's if everything in your spacer system is done right. Okay? I did a lot of work with IGMA before they merged with AMA and all of that, and over the years and things, and spending time at IGMA, the one thing I learned about glass, cleanliness and godliness, okay? Clean glass is the secret. Almost any system out there, if the glass isn't clean, is likely to fail. And when you're washing the glass, a couple of plants in Canada that I'm aware of, hard water is a nasty thing. If you've got hard water and you're not cleaning it up, you will get failures in your glass production because it'll leave a microscopic coating that can cause problems with the sealants on the glass. So the cleanliness of the glass, most important thing. After that, most systems out there designed, if the glass is clean, it's likely going to work. And you know, production issues, there will be failures. Okay, from time to time things go wrong, but the design of most systems out there today, new systems coming onto the market, it's a struggle when you've got a new system that has no field, no time in the field and spacer systems. I can go back 25 years, and the things I said about Super Spacer 25 years ago looks great from an energy point of view, but I haven't seen time in the field. Well, over time, it's proved itself really well in the field and done well. New systems that cross my desk, I get them not as often right now. I used to get one a month for quite a while, but not quite as often now. If they stand up over time, okay, I'm getting close. So spacer system becomes critical. That's argon filling. There's krypton filling. Top line is 70, then 80, and 90 on the bottom line. So one of the questions that crossed my desk is, well, if it's krypton, what if I just fill to a lower rate? Well, if you drop to 70%, there's the 95% krypton line and the 70%, 70%, I got that wrong, 70% krypton, 95% argon. Their performance levels at the optimum spacing are very similar. What I will caution you with about narrow spaces as well. There's another study that was done for NRCan. It needs to be updated before it can be published again because there were some errors in the window program doing the work. Is if the glass collapses at all, you can lose quite a bit of performance. If you already start out and what you can see is if I'm in the argon and I'm at or near that optimum spacing and I move a few millimeters, it's a little bit flatter. If my optimum's here and I get smaller, I start to climb up and get higher U factor right away. Well, it turns out if you get into the prairies, northern Ontario, our cold climates, it can become quite significant. And the other factor is, what was the temperature when you sealed this thing up? Because that's an important key factor. If you're sealing, and talking to some folks in the US, where they're sealing up IG in 95%, or 90 or 95 degree temperature in an unconditioned space, those products should never come very far north. Because you take that product and put it into a cold climate, it can be a really big problem. So that study was done about 2.5 years ago for NRCan. Needs to be redone because starting out with narrow cavities can be very problematic. What have I got left? That just broke down sort of this was a deep dive into what's in there, sort of the solar heat gain range for products that fell into these U factor categories. What was VT ranges, the percent glass. So it was easier to pull out percent glass than percent frame in this part of the study. And you can see the overall IG range. When I get to, these are argon-filled units in casement and awnings, I'm right on spot on that optimum spacing. The only products getting down there, and it was all with 3 coatings of low E. Interestingly enough here, so if you dig into the report, S1, S2, S3 is single silver is 1, double silver is 2, triple silver. And I've seen this in some of my work with clients to get down to that level. Some of the single silver coatings are just off by a little bit and don't make those U factors. You get to double silver, triple silver, you make the U factor at that level. Options that were in the database. It was really quite interesting just to break it all down. When I go, that line there jumps out at you. When you go to sliders, there's nothing on that top line. So that will be the challenge for sure. And the previous one was argon with nothing on that line, and that's the krypton. They're there, but I don't think they're real, is what it comes down to. So last part of the study was, and you won't see this, but I'm illustrating here. I started out with this 85 millimeter high casement window. Okay, it is just this generic window I've been using for a lot of years to compare glass and spacer for clients. I went through 9 variations that got me down to, what was the final number? I think it was 58 millimeters. Yeah, 58 millimeters as the frame height, foam filled with a whole bunch of things gone on in that frame. That one finally got me with a double silver coating to an 8.2. So just went right through all of those iterations, tried foam filling the original frame, a whole bunch. In the full report, this will be fully detailed if anybody wants to look at it. Do not use this as a design. I'm not a good window designer. But it was just to make the point that I will tell you in designs I've been involved with clients, 7 or 8 iterations through that is not uncommon. It takes a lot of work. I'm not sure that window could meet air water structural. And I have no idea whether it will or not. But in the design phase, having people that can do the finite element structural analysis as you're working your way through this is a critical element. That somebody that's doing that work at the same time to figure this out. Where did I see the hand? Okay. So, these design problems, this is an example of PVC. Mike brought up aluminum. All materials are going to be a challenge. I can tell you that aluminum clad wood to get down to those levels, very big challenge. Some of the product that was listed in the database I talked about earlier that was quads with a storm, that might be a way to get some wood product there. Is it acceptable? It's a discussion I want to have offline with Brad because I know you guys offer that. And would that be acceptable to the homeowner? I know from my personal experience with storm windows in Eastern Canada, I don't think I want them. We had single glazed windows with storms for years. They were a big pain in the ass. Sorry, Mike. So this was just an exercise to go through, and it's documented. It will be documented in the report to work through that. But here's the end result of it. Okay, once I got to that last frame, I went back and I modeled doubles, triples with single silver, double silver, triple silver, and interior facing. That's SX in that listing. Interior facing. Which part of this is it? This is the foam filled results. Gives me a wide range of product. But I could also take that same frame now and do it without the film. Without the foam filling. And I've still got a range of products. So that once you're done there, what I'm getting at, whatever you do needs to be scalable. That if you come up with a new design now, changing the stop to handle doubles or triples now gives you some scalability. Adding or putting in foam now later to get to those numbers might be an option, depending. But whatever you're doing, it should be scalable to figure out how to use it now and then scale up for what you may need in the future. I think that's it. Ask me about that photo if you're feeling brave. That's one of mine.
I've got a couple of questions. We spoke about earlier about the offshore windows or European windows coming in, different testing requirements. Is there any effort by the North American or NAFs or anything to get them to change how they test or have to retest here in North America so that they're testing under the same conditions that us manufacturers are as well?
What they're doing right now is in the code, there is this allowance for, I forget the buzz phrase, proving compliance through another mechanism, okay? But it is local jurisdictions get to make that decision. Lots of jurisdictions are accepting that, but they're accepting the energy performance. They're not following up and finding out if the structural performance of the European products meets what's going on here.
So that's a challenge for us North American manufacturers.
It's difficult to codify that and put it into the code to restrict trade.
Why? Well, I'm not saying restrict trade, but why aren't we advocating to make sure that we're all playing on the same level field? Because my next question was, can any of us manufacturers...
Mike, I've been tilting at that windmill for 10 years.
I get it.
Okay.
And so my next question is can we as manufacturers go to Europe, test our windows there, or is there any facility here in North America that tests to those standards and just override it that way?
You could.
Okay.
The cost of doing so might not be something you want to jump into.
I think the cost of having to...
So if you went and did the European testing and
Yes.
had better numbers
Yeah.
on there, you could. It could be challenged. No, I agree with you. I think what needs to be done is educate local building officials.
Yeah, but I think it's unfair because we're getting driven by, political mandates and all that, but then
Okay.
the level playing field is
As much as
incorrect.
carbon content is going to be challenging for the industry, the embodied carbon of a unit shipped from Europe to here will get accounted for. Okay?
But-
The shipping costs, the shipping carbon, let's say, will fall in. But be careful what you wish for.
Yeah, no,
Because everything you build and put in will be looked at.
Wow.
It's going to be a big one.
we don't have in Canada. We're struggling in raw manufacturing, so I think those challenges are not going to be any different because we need to bring in most of our stuff from offshore or Europe with respect to glass. But so you're saying that manufacturers could test the European codes and standards? Could. I'm not saying you're suggesting it, but they could.
Yeah,
and
no,
have
don't
the
say
same-
I suggested
Correct.
that, please.
And have the same level playing field as European manufacturers.
No, because it's not a level playing field.
So
You could do that to.
You're suggesting having Canadian testing plus European testing to say that, look, my European test data is better than their European test data. Interesting theory, but I think we need to push for you need to be tested in Canada.
Yep.
That's what we need to do.
The easy one, Mike, if you wanted to take your product and have it evaluated on the energy scale for Europe, that's an easy thing to do. There are labs, simulation labs in North America that could do that for you. If you had a few reference points on your product to do a comparison and say, look here's what my number is, here's what it would be in Europe, that might be useful in your sales pitch. And that might be a useful piece. Here and then I think Brad had his hand up just when we're done, Terry.
Does the code references what test methods to use?
Absolutely.
So that would, if you're following the code, you have to use the.
Except written into the code, there is a compliance, there is an option for alternative means of compliance. I think that's the right phrase. Alternate solutions. Alternate solutions. But they're one-offs, and they have to be dealt with every local
job.
official. Every job. So it can be done, but it's very challenging. But I've seen some European product with an engineer's signature on an evaluation. Brad.
I think we need to be careful with that because our windows are designed for our tests. They're designing their windows for their tests, and using our existing designs under their tests will not necessarily lead us in the direction that we think we're going to get. So we got to be careful.
Yeah, exactly. One of the biggest difference between the North American and the European standard for energy is the cold side temperature. The European standard uses 0 Celsius. We use -18. You want to go down that rabbit hole? I've got a whole bunch more data we could talk about another time. But what I can show you is if you were in Europe, they design, and that will lead you to wider airspaces. Very common to see 16 millimeter spaces and triples in Europe. That only works in Europe because they don't go any thinner than 4 millimeter glass. If you go to those wider airspaces and trap more volume and you try to do that with 3 millimeter glass, you're going to get more movement of the glass and have all kinds of other issues. So going to those wide spaces that they do in Europe also starts out with a prerequisite of using 4 millimeter glass. It's the thinnest glass they use. So Brad's comment, they design for Europe, we design over here. It's a different game for sure. So you got to be very careful on some of that.
What's the implementation process going to look like? Like, I'm assuming this isn't going to apply to high-rise buildings that need aluminum window wall, curtain wall. What about renovation? BC Energy Efficiency Act has 0 enforcement arm. It gets a little bit, like I worry about the renovation market driving things underground.
Me too.
Because
in a big way.
The consumer, like if you have a bedroom window that you go to a triple glazed casement, it won't meet egress anymore. People are going to navigate this in their own way.
Yeah.
So is this applying to part 9, part 3? Like how is this, being rolled out?
Most
into
of
our
what I
market?
showed here would be part 9. But there's a similar path on part 3 buildings and what's being done there. But on the part 3 side, the prescriptive requirements are almost meaningless because they almost all do performance. Calcs on the, if you're talking high rise, you can't optimize that design unless you do the calcs. So again, some of this, when I talked about capping the solar heat gain, well, that's on the prescriptive path. On part 9 buildings, if you're doing a performance calc and you want to use a higher solar heat gain, you will do that. There's some restrictions in there that's going to make it harder to use that on looking at cooling loads and what's going on in there. Doesn't mean you can't. But if you do, and you go the performance path, it's likely going to push you to a better design to optimize the use of that glass. So those kinds of things, all of what Al was talking about, when you go the performance path, it will begin the process of working with energy advisors to try and do the design. But I totally agree with something Al said yesterday, educating energy advisors on glass and how to select glass, key and critical. Deeper than that, the algorithm for Windows in HOT 2000 is old, and I know so because I helped write it 20 years ago. Okay, so it's a challenge.
Thanks for the great presentation. My question is, like, since I saw this presentation, it seems like 2025 is going to be very challenging. I didn't see any concrete design which will, qualify for those 2025 initiatives what we have for our thermals. And having said that, I mean, redesigning the windows is going to be again challenging.
You bet.
You're playing with the structure. Is it something going to change on wall to door, wall ratio also? I mean, to decrease the size of the window or door or fenestration products?
On residential part 9, there's no restrictions on the amount of glass you can put in the building yet. But when you go down the performance path, the prescriptive path restricts the solar heat gain you can use when you exceed certain levels, but they're not restricting the amount of glass you can put in on the prescriptive path. On the performance path, same story. There's no limit, but it's going to be more challenging as you get more and more glass in the building to hit the targets. And without a doubt, getting to triple glazed with that glass will get you there easier. And we're already seeing that builders doing net zero buildings, even some of the older Energy Star buildings, using triples made a lot of sense. Code requirement windows that would probably succeed in the code in 2025, current Energy Star windows are close. They're real close to getting you there. Any little bit of improvement beyond that, I would say, I can't really say this, but if you wanted a ballpark number for the 2025 code, it's probably a 1.05 U factor, roughly. Somewhere between the 1.22 and the 1.05, it would be right in there, but it won't be prescribed as a prescriptive requirement that way. It's really complex. I would think, Terry, by Windor, there's probably going to be a lot of material out for review on the energy code that we need to be talking about in the fall. And I think there'll be lots more to talk about what's going on for the 2025 code when all the public reviews, because Windor's going to be right in the middle of that public review period, for sure.
Yeah, Jeff, your opinion, since the 2020 NBC's out, published, but we're not yet having to comply with it, not likely till 2024. The 2025 code is only a year and a half away. Can we assume that the 2025 code wouldn't get adopted across provinces until 2027, 28?
No, you can't. They've all agreed to adopt it within 18 months of publication. So I would say mid-2026 would be the latest it would get adopted. Some jurisdictions will adopt it in less than 6 months going forward. Manitoba's been an early adopter. Other provinces, the territories, some of the territories it's almost instant, but that's less of a concern due to sheer volume of construction. But all the provinces have bought in that the 2025 code will be adopted within 18 months of publication. Second mic just for them.
Yeah, exactly. And just want to point out that on the 16th of this month, so BC has their own code review process, and so they're adopting 2020 codes potentially with some modifications. And the public review just opened on the 16th and goes into June.
Yeah.
So that's available on the
I believe
website if you want.
June 16th is the deadline on that one, I
Right.
believe. Yeah. Yeah. And it should be looked at, but they're being quite aggressive, for sure. And so this is their attempt to get the 2020 code adopted.
Is there any concern regarding thermal results and simulation size of windows versus actual measured values? Is that Anton? No, it's Andrew. Values on larger or smaller sample sizes. City Vancouver Energy Modeling Guidelines.
Yes, it's a concern. It's real important to understand that prescriptive requirements set in the national code are based on model size. At the prescriptive level, we should be comparing model size to model size. That's the way they were established and modeled to do all the prescriptive codes in the national code. There's massive amount of modeling to sort of set those levels. They're using the labeled value or the model sizes. When you go into the performance calcs, some of the tools, HOT 2000 has a mechanism where you can put the labeled value in for the window, and when they resize the window in HOT 2000, it'll recalc and give you a different U factor, different solar heat gain, if the energy advisor puts it in that way. Somebody said yesterday, it might have been Al, that they take a lot of shortcuts. Absolutely they do. And I've tried to work with some of them out there that are leading edge and explain, we need to do a better job. Well, to do a better job in the tool right now is a lot more work for them. So it's hard to get them to do it. And they point back and said that NRCan says we can do it this way. Just because NRCan says you can doesn't mean you're doing the best job for the home builder.
And they have no idea on how to deal with mulls or mullions.
Correct. And you and I keep talking about that. We really should get some research done to justify that one. And Terry and I will circle back on that. Because right now, mulls and mullions don't get accounted for in the energy modeling we do. Yeah, they can be.
Okay, any other questions for Jeff? You want to tell us about the picture, the photo?
I should have left it in there. I do some work on water droplet collision. That's two water droplets colliding right there. And if you're interested, I can show you how it's done on my phone. But it's I am a photo geek too, and I love to play with that stuff. That's it.
Thank you very much.
Thank you. Where do you want that? Right here?
Yeah.